Alright guys, we are going to be continuing our journey into Spark using Python. I hope that you were able to watch my first video last week where I covered some very basic fundamentals including data frames and copying objects from RDD. Today we're going to be going into some more Spark related functions such as map and reduce. So let's go ahead and get started here. So first we're going to start our Spark session and also assign a variable to our Spark context. Alright, so what are map functions? Map functions are most commonly used functions when dealing with an RDD object. Some of these include map, map values, flat map, and flat map values. And the map applies a function to each element of the RDD. So each element has to be a valid input to the function. The returned RDD has the function output as its new element. If you have coded in JavaScript before, it's very similar to the map function in that, though if you've watched the videos, Spark has its roots founded in Scala functional programming. So the elements in the RDD object map exp RDD. Below are the rows of the empty cars in string format. We are going to apply the map function multiple times to convert each string element as a list of elements. Each list element has two values. The first value will be the auto model in string format. The second value will be a list of numeric values. So let's see how this works. What we're going to do is we're going to go ahead and use our Spark context. We're going to call it the text file module, and we're going to go ahead and assign it a path to the CSV function or CSV file that we're going to be working on. Then we're going to call it the .take method, which is going to take the first 4 rows of that CSV file. And when we run that, we can see that it successfully extracted the first 4 rows. The first row being the header, which has the column names. So we have MPG, cylinder, displacement, and so on. So now we want to split the auto model from all the other features. So we can do that by mapping through the values. And then we're going to apply a split based on the comma, because this is a comma separated value or comma separated value file. And then we're going to call our .map, applying the lambda function, which was the inline function, saying that for x, we want to return x0 and then x1, index 1, and forward. So you can see when we run this, what we should get is one list of all of the column names, which was index 0 or row 0. So all of those are contained within one list. And then the rest of the values, index 1 and so on, contain the model of the car. And then we have our values here. So index 0, we have the model of the car, and then all of the values associated with it. And once again, here we have the model of the car and all of the values. So what it's doing is it's iterating through for each row of that text file, and it's going to then apply this function, which we say we want to index the first value and then include all of the other values after that as its own unique object. So here, the Mazda RX-4 is the index 0, and then all of the values after it are considered the first index on. So they're their own unique values. But as you can see, we're getting them returned as a tuple. So this is the start of the tuple, where we have Mazda RX-4, and then it it's wrapped here. So all of this is part of the same object. We just have a tuple that contains the model name, and then the second one being this list of all the values. Alright, so now we want to remove the header row. So we can do that by calling it the .first method. So what we're going to say is that our header is equal to our map exp rdd 1.first. Then we're going to create another variable called map exp rdd2. We're going to set that equal to the rdd1, which we defined up here, and then we're going to filter it based on if x not equal to header, which we had defined here. So header was the first row of the CSV file, and then when we want to filter, we want the results to not include that. So what we get is only the actual data that's contained in what you can consider a data frame or a table. So once again, we're getting our Mazda RX-4, and then we're getting all of the values associated with it in its own unique list. So now we're going to go ahead, we're going to use the map function to split or convert the string values to numeric values. So here we call our .map. So for each row in the CSV file, we want to perform this lambda function, which is going to return the first value of that row, in our case the make of the car or the model car, and then we're going to convert the rest of them into a list. Then we're going to map over it, converting to a float every single one of these values. So as you can see up here, when we're working on RDT2 example, we had integers. So what it's doing is it's now iterating for every single row. We're converting this as a list, and then applying a float for every single first index. So the first index being this list of data points. And as you can see, it did successfully convert all of our integers into floats. Alright, so let's talk about the map values function now. So the map values function requires that each element in the RDD has a key value pair structure. For example, a tuple of 2 items or a list of 2 items. The map values function applies a function to each of the element values. The element key will remain unchanged. So let's apply the map values function to this RDD object below. Alright, so first of all, we're going to just go ahead and create a new variable here so that we can use our map values function on it. And we're going to take the first 4 values, which are the first 4 rows. And here we're just going to import NumPy so that we can utilize the np.mean here. And what we're doing is we're now using the map values function and providing the lambda, which is going to convert our data into the mean of all of these different values here. So we're mapping through every single row of our 4 rows that we returned. We have our key value pair, the key being the model of the car, the values being this list here. And as you can see, the model of the car remains unchanged, but what is returned as the first index or second value of these tuples is now the mean because we defined it here. We wanted to perform a lambda function for each x in this map, what's returned from this map values call, We are now computing the mean and returning that. And just one thing to note here is when using the map values, the x in the above lambda function refers to the element value, not including the element key. So flat map. This is a function that applies to each element of an RDD, then flattens the result. We can simply use this function to flatten elements of an RDD without extra operation on each element. Okay, so here we're just creating a list that has 3 tuples in it of different sizes. So this first one has 3, this one has 2, this one has 4. So if you remember in the first video, we used the parallelize function. So we're going to parallelize x, and then we're going to collect this. Now you can see that everything is contained in a list. We have our 3 tuples. Now here we're going to go ahead and use our flat map function and iterating over all of those different values which were contained in our flat map exp RDD variable. We apply the flat map, and what is returned is just a single list with all of the different different values that were in there. So we just have a list now. There's no tuples, there's no separation. It just makes basically our data one-dimensional. Alright, so now flat map values. Flat map values function requires that each element in the RDD has a key value pair structure. So very similar to what we did before. It applies a function to each element value of the RDD object and then flattens the results. So what we're doing is we're maintaining that that key value pair. So what we're going to do in this example here is we have a variable called myData, and we are going to first define our key. So our key is going to be 1, and we have a tuple associated with it with 3 different values. And we can think of this as a row. So our second row, we have an index of 2, which also contains a tuple of 3 values, index 3, and following the same format. So first we must run the parallelize on my data. We collect it here, make sure that everything looks okay, which we do. We have our key value pairs. So when we call the flat map values now, we are going to define our lambda so that we first must convert this to a list, and so that we get a list returned. If we just did a zip, it would return a zip function, which wouldn't actually give any output. So we first convert to a list. We say for the zip list ABC, and then we provide x being the x that we would define here in our lambda. So when we do the flat map values, sorry, that's a mouthful. Flat map values exp rdd1.collect. We now see that we have our index here. We have our the first A of this. So we have first A, 23, the 23 that is represented here. 1B, 28. So it grabs our index, grabs the middle letter now, and then it assigns 28. We have our number 1 index. It grabs the last letter of this list, and then assigns 32. Now moving on to the second row, if you want to think of it like that, we have index 2. Then it starts the cycle over again. So the first letter A, and then it assigns 18. Index 2 grabs B, assigns 29. So what it can do is it's just maintaining that key value pair and then iterating over our I guess, our string of choice here, which was ABC. It breaks it down and then zips together all possible combinations. So we can also unpack these by calling the dot map on it, providing x0 plus the list x1. And now you can see that all the values have been unpacked, and what's returned is now just single list for every single one. So there's no more key value pair. We just have one A23, one B28, and so on. I forgot to run those. Okay, so now we're going to move on to our next notebook here, and this is going to be talking about aggregate functions. Before I move on, let me just go ahead and close this kernel so I don't have any issues. Alright, so first of all, we must initialize our Spark context in our session. So we have two different aggregate functions that we're going to be working with here, aggregate and aggregate by key. So aggregate takes three different arguments here. Zero value is like a data container. It's a structure that should match with the data structure of the returned values from the sequence op function. And sequence op is a function that takes two arguments. The first argument is the zero value, and the second argument is the element from the RDB. The zero value gets updated with the returned value after every run. And comop is a function that takes two arguments. The first argument is the final zero value from one partition, and the other is another final zero value from another partition. The code below calculates the total sum of squares for miles per gallon and displacement in dataset empty cars. So we're still working on our cars dataset here. So we're going to read in our CSV. We're going to use the infer schema equals true, header equals true, and then we're going to select our miles per gallon and displacement. And then we're going to call it the dot take, so we're going to get our first 5 rows. Alright, so in order to calculate the averages, I hope that you guys are starting to understand how we would do so. We're going to call our map function. We're going to iterate over all of those rows. We're going to say for x0, then we're going to call the dot mean method here, which will return the mean of the miles per gallon. And then after we do empty cars df.select displacement, we map over the values, and then we calculate the mean. So the mean for the displacement is 230. So what it's doing is it's mapping over every single one of these miles per gallon. So we have 21, 21, 22.8, 21.4, and 18.7. And then we're calculating the mean, which resulted 20.09. Here, when we call displacement mean, we're mapping through every single row, grabbing all of these values, and then we're calculating the mean based on 160, 160, 108, 258, and 360, which results in a mean of 230.72. Alright, so step 3. We're going to build our zero value, sequence op, and comop. So we're going to calculate our 2 TSS. We create a tuple to store 2 values. So our zero value equals this tuple here, which we just have 0 and 0 in. The z below is going to refer to the zero value. Its values get updated after every run. The x refers to an element in an RDD partition. In this case, both z and x have 2 values. So we define our sequence op as a lambda that takes now 2 arguments. We have our z and x. We say z0 plus x0 minus the mean to the power of 2 is going to be the first value of this tuple. The second value is going to be z1 plus x1 minus displacement mean to the power of 2. So what we're doing here is we're calculating the sum of squares. So the com-op now function simply aggregates all of the 0 values into 1. So now we're com-op equals lambda. We take px and py, px0 plus py0, px1 plus py1. And let's see here, I think I made a mistake and this was supposed to be a cell type here of code. Alright, now let's try and run that. And I got an error. I must have accidentally took something out of this code, guys. I'm sorry. We're going to go ahead and try and figure this out here. Caused by traceback. Looks like we're getting some kind of driver error here from our collect and serve. Alright, we're going to go ahead and move on here. I'll try and debug that later before I post this on GitHub. So we're going to go over the aggregate by key. So this one takes 0 value, the sequence operation, and the combined operation. This is very similar to aggregate. The aggregate does all results to the very end, but aggregate by key merges results by key. So here we're going to import our data, which is going to be the iris dataset. So as you can see, we have our headers here, which are sepal length, sepal width, petal width, and species. And then we have our first row of our data points. So we're going to transform it first into a tuple RDD by using our map function. We're going to split it based on the commas. And then we want to get rid of anything that says sepal length. Now we're actually going to do a map over the data set. We're going to take the last item, and then we're going to convert to float and do all values to the end. So when we do our take 5, we now maintain our key value pair. So our key was Setosa. So we grab the last item here of our list, which was the species, and then we return the values associated with them. So we define our initial values, our sequence op and combined op. We're doing our sum of squares here, so we're saying for x0 plus y0 to the power of 2, and we have x1 plus y1 to the power of 2. And then we're combining them here with x0 plus y0 and x1 plus y1. Now when we do our aggregate by key and we collect them, we now have our species. We have aggregated all of the values, and what's returned now is 1,259. So it gives you a grand total of our sum of squares for all of this data. Alright, now we're going to go into continuous variables and categorical variables. Once again, make sure we start our Spark session. Alright, so there's two functions we use to split a continuous variable into categories. We have the binarizer, which splits on the column based on a given threshold, and then we have the bucktizer, which is it splits a column on continuous features into categories given several breakpoints. With n plus 1 split points, there are n categories buckets. So we're just going to create some data here, some random data using NumPy. And we're going to create a data frame using the Spark to create data frame PDF just so we can visualize it. Okay, so we have two columns, x1 and x2, and then we just have our dummy data contained within. So we're going to go ahead and binarize the column x1 and bucketize the column x2. So first here we have to import our binarizer and bucketizer from PySpark.ml.feature. We're going to import the binarizer and bucketizer. We define our variable for our binarizer. We set a threshold. We set our input column, and then we want to have our output column. So that's where our binary input, or I'm sorry, binary data is going to be put. Here we have our bucketizer. We define the splits at which we want to actually create them. Here we're defining as 0, 2.5, 5, 7.5, and 10. So we have to give it the input column, x2, and then we have the output column, x2 new. So now I'm going to go ahead and just create a pipeline so that we have both our binarizer and our bucketizer. So from PySpark.ml, we import our pipeline. We say the stages is going to be equal to binarizer and bucketizer. Pipeline, we call the pipeline method, and we define our argument as stages. So stages equals stages, and then when we fit the pipeline using our data frame, we then call the .transform method. So we fit on the data frame, and then we transform the data frame, which is going to result now in creating two different columns, one for our binarized data and one for our bucketized data. So you can see the difference here. So we had, for the binarizer, we had a threshold of 0. So we have some negative values here. If the values were below 0, they were given a 0. If they were bigger than 0, they were given 1. So true or not true, or on or off. So the x2 new, let's describe it. Let's explain this one a little bit. So what we did, x2, we had data that was all over in a range between 0 and 10. So we created these buckets. So from 0 to 2.5 is one bucket. From 2.5 to 5 is another bucket. From 5 to 7.5 is another bucket, and 5 to 10. So we should have a total of 4 different buckets. So as you can see here, our value 6.83 falls within the bucket of our third bucket, but it would be index 2. We start at 0. So it's in the 5 to 7.5 bucket. So you can see here there's 1 bucket, 2 buckets, and 3 buckets. So we give it a 2. Likewise, 7.12 also falls within that same range of 5 to 7.5, so it is also classified as a 2. 3.7 falls in between our second bucket here, 2.5 to 5, which is going to be index 1 or our second bucket, but due to 0 index, and we give it a 1. So you can see now that our data has been transformed into binarized representations of our data based on these buckets that we defined up here. Alright, so we're going to go over a little bit of machine learning here and kind of get a sense of how we can do a data check. So first we're going to import our data. We're going to import it from Kaggle, It's a Titanic data set. It's a very popular machine learning data set where you can predict which passengers were going to survive and not going to survive. So we have all kinds of different data here. We have our labels, survived 0 or 1. We have the names, the age and sex, and so on. Okay, so first let's just kind of dive in and see our data types here. So when we use the print schema method, it's very similar to the schema information that we use in SQL, where we now see the name of the column, the type of the column, and then we also see if it's nullable or not. So we can see the length of the columns, we can see the count, or n, or number of observations. Alright, to summarize the columns, we'll just make this handy function here, describe columns. So for I in df.columns, iterating through each of the columns, we print the column plus I. Titanic.select I.describe.show. So when we run that, we are getting this handy little summary of every single one of our columns. So we have a passenger ID, we're getting our count, our mean, our standard deviation, the min and max. So it's very similar to the pandas.describe. So I hope that this doesn't seem like too far of a stretch. As you can see, and we keep kind of noticing now that there's a lot of similarities between Spark and some of the pandas features. So how can we find columns with missing values? So here we're going to define a function. We're going to say the number of rows equals df.count. And then we say for value in df.columns, or v, summary df. So we select v and then describe it. We do a count with summary df.collect, the first one, index v. So we're iterating through, so that's going to constantly change. And so if v is less than the count, the number of rows, then we know that we must be missing a value. And then here we're just calculating the missing percentage by dividing by the number of rows and then multiplying by 100 so that we actually get a better representation. When we run that, so we're going through each column, seeing if there's any missing values within the data, and then returning a percentage based on what we've found. Okay, so we're going to go into how can we make subsets of our data. We know how to make our context and Spark session, but now we're going to go back to working with our car CSV. So what we want to do here is we want to add an index to our RDD elements and then have the index with the associated values that come with it. So we have an index here of model, we have the model of the car, and then we have all of the associated values that come with it. So when we call zip with index, we take 5. You can see here we have each row, their index, and then the values. So now we're going to apply the map function to modify the structure of each element. Assume x is an element from the above RDD object. X has 2 elements, x index 0 and x1, x1 being the values. x0 is a row object, and x1 is the index, which is an integer. We want to merge these 2 values to create a list. So what we want to do is take the first element in the list as the index. Okay, so we called our zip with index method. We iterate through every single one of the rows using map. And then we're going to concatenate them here. We have x1 plus list x0 and then dot take 5. So what we're doing is we're kind of joining all of our data together. So we now have our index of 0, 1, 2, 3, 4, and then model of the car, and then all the values associated with it. So let's add column names and save the result. So header equals index plus emptycar.columns. emptycarsdf equals emptycars.rdd.zip with index. We map over each row, and we provide this lambda here. Then we call the .2df at the end, and we provided the header. So here now what's returned is this data frame now, where we have our index and we have our model name and so on. So to select specific rows of this, we can say if the index is in range 1, 2, 4, 6, and 9, we want to show them. So by calling the .isIn, and we're filtering, we only get those returned indexes. To select rows between the range, we can say .filter our data emptycarsdf .index.between. So we want to get the value or the rows between index 5 and 10 and return them. There's also a cutoff index, so we want to filter all the rows with the index less than 9. So here you can see we have index 0 through 8. We have greater or equal to 14 here, so it's going to return every single value that is greater than index 14. And we can also select rows by using logical criteria. So if we want to filter emptycars.cylinder equal to 4, .show, and we can see here that our cylinders all equal 4. So this is very similar to like performing queries or df.queries in pandas, or even using like df.loc, and then applying a logical criteria on which we can return our data. And filtering is based on multiple conditions. Example, for vs equals 1 and am equals 1, we use the conditions to build a new Boolean type column. We filter the data frame by the new column. So to help us do this, we're going to import functions as f from PySpark.sql. And one thing to note here is when passing multiple conditions to the when function, each condition has to be within a pair of parentheses. So here we're saying f.when when the car's vs is equal to 1 and the am is equal to 1, that name filter column, oops, empty cars df is not defined. Did I stop running cells up here? I think I did. Here, let me run these real quick. Alright. There we go. Okay, so the case when vs equals 1 and am equals 1, then 1, end as filter column. So we're creating a new column based on those specific criterion. Here you can see our filter column. We are getting some null values, meaning that they were not found to be a match, and you can see 1 representing that it was in fact a match. So now we can filter the data frame by these requested conditions. When we filter the data frame, we can drop the filtering column. So what we've done is we've filtered the data based on a specific subset, based on a specific criteria, thus reducing the amount of data that we have to work with. So we are only returning what we want and what we are interested in. Alright guys, that's going to wrap it up for this week's video. Next week I'll go ahead and continue. I've put together quite a few videos here with Spark, and I hope that I'm giving you guys a little bit more background than what you can find in the course. Feel free to shoot out any questions or comments. I'm pretty much always available on Slack. Just feel free to shoot me a text and we can discuss any issues that you're having. I hope everyone is having a great week and we'll talk soon. Take care.